Hey guys, hi, welcome back. So today we will start the chapter 4, Moving Charges and Magnetism. So already in the electricity part, we all know that whenever charge is rests, then we see electric field around it. So in this chapter, what we will discuss is that whenever charge will move, then we will have magnetic field around it as well. Along with the electric field, we will have magnetic field. So this is what the chapter says, then moving charges and magnetism. That is, whenever charge will move, it will have electric field and magnetic field both around it. So to understand this, firstly we will discuss about the Oersted experiment. Okay, the Oersted experiment. So it was in 1820 that Oersted, when he was performing an experiment, so what he saw that whenever current was flowing through a wire, he saw that the magnetic needle was showing deflection, and the deflection was noticeable for a moment. So he came to the conclusion that when current was flowing through the wire, there is a deflection in the magnetic needle. So magnetic needle shows the deflection only when there is magnetic field around it. So he came to the conclusion that a straight current carrying wire, suppose if we have a current carrying wire and current flows through it, then we will see magnetic field around it, because he said that charges current flowing means charge moving, right? Charge moving. So he said whenever charge will move, it will have electric field and magnetic field both. And magnetic field is present. It was evident by the deflection of the needle. So this could be explained in a way. Suppose we have a wire connected with a cell. Okay. Suppose this is a wire connected with a cell. This is the negative terminal. This is the positive terminal. And we know current flows from positive to negative terminal. So here a magnetic needle is placed. Suppose this is the north and this is the south direction. So whenever current is flowing through south to north, the deflection is in the left side. On the other side, we can say this deflection is in the direction way west. Okay, this is north, this is south, this is east, and this is west. So Oersted said that whenever current flows, needle shows deflection, and this deflection is in which direction? This was given by Ampere's swimming rule. Okay, it was Ampere who gave the swimming rule, and he said that whenever current flows south to north, then deflection is over west. So this can be remembered by the word stone, that current is flowing through south, and this is what north. Okay, and O is for over, and W is for west. So whenever current flows through south to north, then the deflection is over west. So now the swimming rule. How the swimming rule can be explained using this? Suppose we have a man swimming. Okay, we have a man swimming. Suppose these are the feet. This is feet of the man. Just assume it. Okay, these are the hands. So if you see, if a man is swimming, we know he is just reversed. So when a man is swimming, and if we take his feet to be south and his had to be in the north direction. And if current flows, okay, if current flows from south to north, then the needle will show deflection towards its left hand, that is towards the west direction, right? So this is what the Ampere swimming rule says, that whenever, if we assume that current flows from south to north, then the deflection of the needle will be over west. So this is how we can get the deflection of the needle's direction. All right, so this was the beginning, that whenever current carrying wire is there, we will see deflection, and that deflection will be towards the west when current flows from south to north. All right. Now, next, what it came to the conclusion that there are various sources, okay, of magnetic field except magnet. That is a current carrying conductor, which can be modified, and you can say moving electron also produces magnetic field, moving charge particle also. This all the three statements are same, but you can might get in MCQ options. So you can choose all of the three, okay? Now, when we have discussed that there is magnetic field around the straight current carrying conductor, let us see what is magnetic field. Let us define magnetic field. So we all know what is electric field. When we were discussing electric field, we say that it is the region around a charged particle, right? This is how we explain electric field. So the same goes with magnetic field. Suppose we have a magnet, or you can say a straight current carrying conductor, because current carrying conductor also has magnetic field around it. So whenever a magnet or a current carrying conductor is there, then there is a space around them. Okay, there is a space around it. And within that space, if you bring any magnetic material or magnet, then the magnetic effect can be felt. Suppose if you are having iron filings, okay, iron pieces at this place, it is out of the region, right? It is out of the space. This iron pieces won't experience any force. But whenever these iron pieces are sprinkled here, then it will feel the magnetic effect, because it is in this region, and this space around a magnet or current carrying conductor is said to be the magnetic field. So the simple definition is that magnetic field is nothing but the space around the magnet, or you can say a current carrying conductor, within which its magnetic effect can be felt. Okay, so the unit of magnetic field is Tesla, and it is denoted by capital T. The Cesius unit of magnetic field is Gauss, denoted by capital G. And you need to remember that 1 Tesla is 10 to the power 4 Gauss. And 1 Gauss will be eventually 10 to the power minus 4 Tesla. So these are the units you need to remember. Tesla is the SI unit and Gauss is the Cesius unit. Now let us see how we can calculate the dimension of magnetic field. We all know to calculate the dimension. We have done in class 11th. Okay, so now here when we will see the magnetic force is given by F is equals to BIL. Okay, later on we will see the derivation, but now let us see F is equals to BIL. So here if you see, if you can write F by IL, it is equals to B, that is the magnetic field. And we know the dimension of force, it is mlt minus 2. How we can see? Because force is mass into with acceleration. This is how we write. For mass, it's m. Acceleration is meter per second square. So L t minus 2, right? And for current, it is ampere. And for length, it is L. So you can write the magnetic field dimension would be m L0 T minus 2, A minus 1. So this is how we can calculate the dimension of magnetic field. Clear? So in this part we saw what is Oersted experiment, Ampere streaming rule we saw, and magnetic field. Okay. Next what we will see that how we can know the direction of magnetic field. Okay, suppose if you're having a straight current carrying conductor, or sometimes you might have a closed loop carrying current, or you can say circular coil carrying current, then how you will know the direction of the magnetic field? So firstly, you need to remember whenever you have a straight current carrying conductor, okay, if your current carrying conductor is straight, then you will know the direction using the Maxwell's right hand rule. So what the Maxwell right hand rule says, that if you are holding, okay, a current carrying conductor in your right hand, okay, such that your thumb is in the direction of current, okay, thumb is in the direction of current, then your wrapped or curled fingers will be in the direction of what? Magnetic field. It's very simple. Suppose this is a conductor and the direction of current is here. So if you hold this with your right hand, if you hold this with your right hand, you will see your curled fingers will be what? This way. If you hold it and check it out, you can just see this side, it will be the magnetic field is inward, this side it will be outward. Just you can see. Check your hand, put your thumb in this direction. Point your thumb in this direction. Similarly, if you take your thumb to be in this particular direction, you will see this side the magnetic field is inward, this side is outward. You can see this side your curled fingers will be going, this side your curled fingers will be going inside, this side it will be outside. Okay. Similarly, if you have in this direction, in this case, what you will write? This side it's inward, this side it's outward. Okay, so this is how you can see. Very simple, just take the direction of current towards the thumb and you'll get it. Okay, next in a closed loop carrying current. So in case of closed loop carrying current, we will use the right hand screw rule. Okay, right hand screw rule. So what it says that if you are holding a screw in your right hand in such a way that the rotation, the direction of rotation of the screw is in the direction of what? Current. then the direction of motion of screw will give the direction of magnetic field. So this you can directly know that direction of rotation of screw means either the screw will rotate clockwise, right? Or it will rotate anti-clockwise. Okay. So you can take a simple example if you are using water bottles. Okay. The same concept you can use. If you have water bottle, you can see whenever you want to open the water bottle, you're always moving it anti-clockwise, right? You always move it anti-clockwise. So you can just take a bottle and try it out. To open the cork of the bottle, open, you always move the cork into anti-clockwise direction. So in your anti-clockwise direction, if I take in your anti-clockwise direction, the cork opens. Okay, the cork is opening means you see anti-clockwise movement of the cork is the direction of current. And the cork opening, that is the motion of the cork, that is the motion of the screw, is outward because your cork opens, right? So whenever the current is in anti-clockwise direction, then your magnetic field is always what? Outward. Okay, dot represents outward. And whenever you want to close the cork, in that case, that is in clockwise direction. Okay, you always rotate it in clockwise direction. Then it's inward because at that time you will see the cork will go inside, it will get fixed. So it is always inward. So you can directly remember that when the direction of current in a circular loop is clockwise, then the magnetic field is inward. And when it's anti-clockwise, your magnetic field is outward. Clear? So it's very simple. You can remember the direction of magnetic field in a straight current carrying conductor is given by the Maxwell's right hand rule, thumb rule. And in case of closed loop carrying current, you can just calculate your direction. You can see the direction is in the corkscrew rule. All right. So now we will see three important points. So you need to remember that when you have a straight current carrying wire, okay, when you have a straight current carrying wire, suppose this was the wire, okay, the magnetic field was inward this side, right, and outward this side. Okay, that means it was something in this way. Inward this side, outward this side, right? This way. Inward this word, side, outward this. So these are in the form of what? Concentric circles. This is in the form of what? Concentric circles. So whenever you are having a straight current carrying conductor, the magnetic field is in the form of concentric circles. Next, whenever you have a circular coil carrying current, suppose this is circular coil carrying current, it might be anti-clockwise or it might be what? Clockwise. Either. So here it was what? In terms of clockwise, it was always outward, right? And in case of anti-clockwise, it was outward. In clockwise, it is always what? Inward. Just a second. It is always inward. So in this case, what you will see, the magnetic field is always straight line. Suppose you see this is a circular coil. So the magnetic field will be what? This way and then round. This way and then round. So though it will take a turn, but if you see here, it is always in the form of what? Straight lines. Okay. It will go and get joined somewhere. It will go and take a round somewhere. But now if you see, it's always straight lines. You can visualize it using a bangle or any circular object. Now you need to see the third point that both the current and the magnetic field are perpendicular to each other. And it's true. If you see here, if current is flowing in this direction, if you take this to be the current, small current element, you can see the magnetic field. This is the magnetic field. So these are always 90 degree perpendicular. In this case also you can see if this is the magnetic field, this is the current element. So this is what? Perpendicular. So current and magnetic field are always perpendicular. One more thing I can say you, if you're having a circular coil, okay, in this also you can use the right hand thumb rule to see the direction of current. It's inward or outward. Just take a small elementary length, small length if you take, and if you see here, if we put the right hand thumb rule, this is the what? This is the direction of current, that is the direction of thumb. So this is inward this side, outward this side. So current is outward. Similarly, if you consider anti-clockwise this way. So if you see in this direction, if your thumb you're pointing in this direction, this will be what? Inward this side, outward outside. So you can see and clockwise it's inward, anti-clockwise it's outward. So you can use the right hand thumb rule in circular coil also. But perfectly it's used in the these cases we use the screw rule for circular loop. So in this video, the very first introduction, what we saw is that the experiment which gave us the indication that current flowing, okay, if wire has current flowing, it will show magnetic field around it as evident by the deflection of the needle. We have the ampere swimming rule, which gives the direction of the magnetic field. That is, when current flows from south to north, deflection is towards the west. That means whenever a person is swimming, and if you assume that current is flowing from his feet to its towards his head, and feet we have taken south pole, his head we are taking the north pole, then the deflection is towards its left hand. Okay, it is towards its left hand. Then we have seen that there are different sources of magnetic field. Okay, for the production of magnetic field, except magnet, that is, we can say current flowing through the wire, or you can say moving electron or moving charge particle. Then we have seen the definition of magnetic field. It is a space around a magnet, or you can say current carrying conductor. Unit we know is a CGS unit is Gauss, SI unit is Tesla. Dimension we have calculated. We have seen the direction of magnetic field as well, both in straight conductor and current carrying circular current, a circular loop carrying current. So that's all in this video. Thank you so much. In the next video, we will discuss about the Biot-Savart's law. So I would suggest all of you just read this entire theory well, write it down, and that will help you a lot. Have a good day.